All right. So we spoke about enthalpy. Oh, we got to finish up enthalpy. I'm sorry. We didn't finish up enthalpy, so I do want to work a little bit more on that today. Okay, so the idea with enthalpy and the symbol for enthalpy is H, is that we generally don't measure enthalpy. We don't measure H. So we don't measure it like if I said, what's the distance from New York to Los Angeles, 2,471 miles. You would measure that distance. That's a number. There's a number to that. Typically what we do with enthalpy is we measure differences in enthalpy. So I might say, a chemical reaction has a certain amount of energy. Then it reacts, and now it has a different amount of energy after it reacts. What was the change in energy that it has during that reaction? So we're looking at changes. So typically we're interested in what's called the change in enthalpy. And so that would be delta H. Now that's a kind of it's an awkward name for something. So it's not like velocity. We understand what velocity is. Change in enthalpy is awkward. So we just refer to it as heat. Okay, so you'll see terminology in these problems: heat of reaction, heat of combustion, heat of solubility, heat of solution, stuff like that. Heat is referring to enthalpy, change, delta H. So essentially it's based on the following idea. If you have a chemical system, so, you can imagine this could be a battery, or it could be, an engine in an automobile. There's a certain amount of energy in the fuel. There's a certain amount of energy in the oxygen in the air. Altogether, there's a certain amount of energy. So it's got energy. And some of that energy is going to leave, right? And typically it leaves in the form of enthalpy. Okay, so there's a change in enthalpy that occurs during this process, right? Now, because of the way enthalpy is defined, it's defined in a very specific way. It's defined at constant pressure. We went through the derivation of this last time. The enthalpy change for any kind of process is equal to just how much heat goes into or out of the system. Remember, we have the system. That would be the battery. The system could be the engine of a car. And so we put a little P here to indicate it's at constant pressure. Okay, and what that does is it makes things really easy to measure and calculate. All we have to do is measure the heat that goes out of the reaction. So imagine a candle burning. If you got a candle burning, it's giving off heat. All you do is measure the amount of heat that's coming off of that candle from the flame. And if you can measure that heat, you now know what the enthalpy change of that candle, of that whole process of the burning of a candle is, right? And the reason that works is that under constant pressure, it's not really doing any mechanical work. The candle's not doing any mechanical work. So we're set. Okay. So that's our enthalpy. So this is something that we tabulate, we measure, we study, we're interested in it, and we'll talk about how we get the values when we get to calorimetry. We also looked at this issue that you could manipulate equations, right? So if I said, hey, I have this reaction, A goes to B, and it has a certain delta H, I could actually figure out what delta H is for the reverse, right? So if I say B goes to A, that's the reverse of A goes to B. Well, then you just change the sign. It becomes negative delta H. So that's kind of cool. You can figure that stuff out. And then we said, hey, what happens if you multiply the equation by some number? So I went from A goes to B to 2A goes to 2B. Well, you just take 2 times delta H. You just take whatever number you multiplied the equation by, you multiply delta H by the same amount, and now you know what delta H is. That's kind of cool too, okay? So those were sort of the background. Now, let's take a look at another aspect of enthalpy. And this is really kind of getting a little bit closer into what chemists are interested in. And that is calculating what's called the heat of reaction. So save that one. So new whiteboard. So calculating the heat of reaction. Okay, so the way this works is we start with a thermochemical equation. Okay, so the thermochemical equation that we're going to start, this is the combustion of methane. This is a, pretty famous reaction. This is when you burn natural gas. This is what you're doing. You're taking methane, using the oxygen that's in the air, combusting it into carbon dioxide. You hear a lot about carbon dioxide these days, right? With climate change and all of that. Carbon dioxide is, it absorbs infrared radiation. So it does trap heat in the Earth's atmosphere pretty efficiently. And so that's the chemical equation for the combustion of methane. But to make it a thermochemical equation, we need to know what delta H is. So minus 882 kilojoules, sorry, kJ. So the units of thermochemical reactions are typically kilojoules, all right? So there we go. So there's a couple of questions that Alex is going to ask you. The first one, is this endothermic or exothermic? And that's the easiest one. That's easy, right? So when you take the test, you get this one right for sure. So our convention is that for heat or for enthalpy, it's the same convention. If this is negative, it's exothermic. If it's positive, it's endothermic. So the logic behind this is that if it's negative, it's losing the heat, right? So it's like a bank account. If you give someone $882, you've lost that amount of money, right? It's going out somewhere, right? So negative means exothermic. That's the easy one. Okay. Now the next one is just a little calculation. So now they say, suppose 69.4 grams of methane react. Will the heat be released or absorbed? Okay, now that's a simple answer to that one too. That's really just kind of testing whether you understand the sign convention. The sign convention means that heat is released. Negative means released. Absorbed is positive. Absorbed means you're taking, right? So like a sponge absorbs water, it gets heavier, right? It has more water, so it has more mass. Same thing with heat. As you release heat, that's negative. As you gain heat or absorb heat, that's positive. So they give you a number there, 69.4 grams of methane, but that doesn't matter how much. That's just going to determine how much heat is actually released. The sign is what determines whether it's absorbed or released. Okay, so you don't have to worry about the number to answer if it's absorbed or heat or released. Changing the mass of something doesn't change it from being endothermic or exothermic. So since it's exothermic, that's what determines that it's going to be released. So that sign convention, the negative, that tells you the first two parts of that question. Okay. Now, this leads you into the third part. The third part of the question is, okay, how much? So that's the third part. How much? How much heat? Right? So now what they're saying is that this reaction produces this amount of heat. So you might say, well, wait a minute, there's the amount of heat right there, minus 882 kilojoules. Isn't that the answer? And that's not quite right. And it's not quite right because if you think about it, we do need to fill up our cars, unless we have an electric car, with gasoline, right? And the more gasoline you put in the car, the further you can drive, the more energy you have, right? Gasoline has a certain energy content. You can almost think of the energy content as like the enthalpy of the gasoline. So then what happens is you use the gasoline, you're losing energy, right? It's going into heat, it's heating up the environment, but it's also doing mechanical work to move your car. So we do know intuitively that if you put 1 gallon of gas in your car, you can't drive across the country. You don't have enough energy content, right? You don't have enough enthalpy content. So you do need to have more gasoline. So that's what this number is all about. It's saying this is the amount of fuel. In fact, methane is a fuel. You could run an automobile on methane, and it's something you could do. There aren't very many vehicles that use methane, but some of the buses use compressed natural gas, right? CNG they call that, and that's essentially methane. So the amount matters, right? The amount of fuel you have matters in terms of the amount of energy you can get out of the reaction. So what we're going to do is we're going to connect this number here to this number that's given right here. And so here's how you do it. It's not obvious, but if you look at the thermochemical equation, there's stoichiometry involved. There's moles in there. So the methane is really, it has a coefficient of 1. So we'll think of that as 1 mole. Okay, so if the balanced equation has no number in front of it, that means it's 1. So we're going to call that 1 mole. So we're going to say that in this reaction, 1 mole of methane, and then there's a 2 here, right, in front of the oxygen. So we could also say that that reacts with 2 moles of oxygen. Now notice I put an equal sign in there, and that could be confusing too. You might say, well, wait a minute, methane is not equal to oxygen. That's true. It's not the same stuff, but they are related to each other mathematically, meaning that every time that 1 mole of methane reacts, 2 moles of oxygen also reacts. So we'll use the equal sign to give us a mathematical relationship between how much reacts. And you can do the same thing with the products. There's no number written in front of the CO2, so 1 mole of CO2. And there's no number, or there is a 2. There's a 2 in front of the water, so 2 moles of H2O. Now you don't need all that information to do this problem, but I want to show you the idea. The idea is that those are all equal to the amount of heat we're going to release. Okay, that's the important part right there. The equation, the thermochemical equation, gives you the relationship between how much of each of the chemical materials in the reaction relate to the amount of heat that you get out of the reaction. And that's kind of cool. That's like, it's almost like a miles per gallon. It's telling you can get 30 miles for every gallon. 1 gallon is the amount of fuel, right? 30 miles is distance, but in a way, if you think about it, in a car, distance is really, it relates to energy, right? Like if I know intuitively that if I can drive 30 miles, that requires more energy than driving 15 miles. They're proportional in some sense, right? So that's what this equation does, the thermochemical equation. It gives us the amount of fuel or the amount of products that are related to the amount of energy with the reaction, okay? So the larger that number is, the more energy you're getting out of the fuel. So if I did the same thing with C2H6, a different organic compound instead of methane, I'll have a different number. So it has a different energy content. And engineers study that all the time. How much energy content does something have? So it turns out most chemical reactions that we use have about the same amount of energy content. They're within a factor of 3 or 4 of each other. So there's a limit in terms of chemical reactions. You can make high energy chemical reactions, but you can't make them 100 times more powerful. So that's why technologically, we've kind of reached a limit with how great our batteries are. Our batteries are limiting us now. We can't have an entire supercomputer on a phone because the battery just can't produce enough energy in order to deal with that. So you have to plug it into the wall to get more power out of it, right? So you have to go to something else like nuclear power. Nuclear power could produce 1,000 times more energy, but nuclear power unfortunately produces radioactivity, which is actually pretty dangerous. So that's why we're for the most part stuck with chemical reactions. Okay, so now here's how you deal with it. You don't know how many moles of methane you have. You know the number of grams though. So I'm going to write that number here: 69.6 0.4 grams of methane. Okay, and what I'm going to do is, since my thermochemical equation it's all in moles, right? Those are all in moles. What I'm going to do is I'm going to convert this grams of methane to moles. And you haven't done this since chapter 3, I think. So you probably forgot how to do it, or you might have forgotten how to do it. Let's convert it to moles. 1 mole of methane. Remember, to go from grams to moles, you divide by the molar mass. The molar mass of methane is 16.05. Right? Because carbon's 12, hydrogen's 1, so that's 16. But carbon's really 12.01 and hydrogen's really 1.01, so that's 16.05. And that's going to give us the number of moles of methane. Okay, so let's come over here. I'm going to pull up my calculator. 69.4 divided by 16.05, and you get 4.324. Uh-oh, there we go. 4.324 moles of methane. Okay. Now, here's the step that may not seem intuitive to you, but this is how we're going to use it. What the thermochemical equation tells us is that every time 1 mole of methane reacts, 1, right? That's the coefficient is a 1. This is how much heat you get out of the reaction, 882. So if I had 2 moles of methane, I would have twice as much energy, right? Twice as much enthalpy. If I had 3 moles, I would have 3 times as much energy. If I had 4 moles, I would have 4 times, right? 4 gallons gives you 4 times the distance as 1 gallon of fuel. So same thing here. So what I do is I take 4.324 moles of methane, and I say, hey, it's 882 kilojoules for every 1 mole of methane, right? 882, negative 882 for every 1 mole. So I'm just writing the 1 mole down here and the 882 up at the top. And then your moles of methane, right? So think about it logically. 1 mole is 882. 2 moles would be twice as much. 3 moles would be 3 times as much. 4 moles would be 4 times as much. Well, this is a little more than 4 moles. So it's a little more than 4 times 882, okay? And so it shouldn't change the sign, right? In part B, we said, no, it's still going to be exothermic. It doesn't matter how much methane is reacting. It's still exothermic. That's the sign, negative. Same thing here. We're still going to have a negative because changing the amount, changing the amount of the reactant is not going to change the nature of the reaction. So 882 times 4.324, and you get negative 3,800. I guess we'll do 3 sig figs, 810 kilojoules. Now, oddly enough, there's a significant figure issue that Alex might give you an issue with, which is that 0 is ambiguous. That 0 might be significant or not significant. So the way you deal with that is you do scientific notation. So you move this over 3 places and you get 3.81, right? So that's 3 sig figs right there, but you moved it over 3 places, so you have 10 to the 3 kilojoules. So that you might need to do that to get the right number of sig figs, okay? And there you go. So had the question been a little bit different, suppose the question said it was 69.4 grams of water was produced. How much enthalpy is going to be associated with that reaction? Then you would say, okay, we're going to relate 2 moles of this to 882 kilojoules. So we would say, okay, 69.4 grams of water, H2O, and then we would use the molar mass of water, 18.02. That would give us the moles of water here. And then we'd say, okay, moles of water times 882 divided by, and be careful, water has a 2 in front of it. So if this whole thing was, with water, you'd have 2 moles of water. So you'd say minus 882 kilojoules per 2 moles of water, right? Because the 2 is over there. And then you'd need to know your moles of water. So you can do it with any reactant or any product, but to be honest with you, in combustion reactions, people are most often interested in how much energy you get out of a certain amount of the fuel, right? The fuel is the methane. So you typically wouldn't see oxygen or water, carbon dioxide in this calculation, but you could. I mean, it's certainly perfectly fine to be able to do it. But the main thing you would be doing it is with fuel. And if you remember, combustion requires really like three things. You need a fuel, right? So that would be your methane or gasoline. You need what's called an oxidant, an oxidizing agent, right? So that's typically O2. And then you typically need some sort of spark. So you need an ignition. So that's why internal combustion engines, our traditional cars, have spark plugs, and you need to have a battery, right? The reason you need a battery is you need the electricity to start the car. Once the car is starting, it's not really using the battery anymore. In fact, it's charging the battery after it starts. But you need to start that car. So you need an electrical source to spark the reaction. And that occurs via a spark plug or multiple spark plugs. So you need an ignition. Once the reaction is ignited, it's self-sustaining. You don't need to keep adding ignition. It keeps going on its own. You also need fuel, and then you also need the oxidant. Okay. Actually, I made a mistake. That's not true. The spark plugs are used to ignite the fuel in the cylinders as the reaction is going along. So that electricity is produced by the automobile, by an alternator, but the actual starting of the car is done with a starter. That's a separate circuit that uses electrical power from the battery to ignite, to start the engine up. So it's not actually the spark plugs that are providing the energy to start the car. It's actually the starter. Okay. All right. So that's a pretty standard calculation. Okay. And that's, I'm going to show you one more example just because it's such a common example of what we do. Okay, so let's take a look at this one. So this one is not combustion. This one it's a redox reaction. The highly energetic reactions are almost always redox reactions. So this is not one that we would typically use for producing energy, but it is energetic. I'm sorry, 184. Okay. So 54.8 grams of Cl2 react. And then we want to know if it's exothermic or endothermic. We want to know if it's released heat or absorbed heat. And then we want to calculate delta H given this amount right there. Okay. So let's take a look at it. Again, endo-exo, that's easy. You just look at the sign right there. That's negative, so it's exothermic. The sign is negative, so that means energy is released. You can use this to get heat out of the reaction if you want to use that heat. Okay. Now we calculate delta H. So we have 54.8 grams of Cl2. So what I'm going to do, just like the last time, I'm going to convert that into moles. So 1 mole of chlorine, excuse me, chlorine is 35.45 grams per mole. So dichlorine, Cl2, would be twice that, 70.90 grams. So that's your molar mass, okay? So it looks like we have less than a mole, right? The previous one, we had 4.3 moles. Now we're going to have less than moles. So 54.8 divided by 70.90, and you get 0.77 I'll keep 1 extra sig fig until we finish this up. Right, so that's a good strategy, right? Keep 1 extra sig fig. We only need 3, right? This only has 3, so our answer is going to have 3. But you keep 1 extra until you do the final step. So now we say, okay, this is the amount of delta H for 1 mole, right? That's a 1, so that's 1 mole, so that's easy enough. So 0.7729 moles. And then it's minus 184 kilojoules for every 1 mole, right? You're trying to get rid of the moles. And you're trying to find delta H, so because it asks us to find delta H, okay? So times 184, and you get negative 142. Let's round it to 3 sig figs. And there's your answer, right? Still exothermic. The amount doesn't matter in terms of that. It just matters in terms of how much energy you're going to get out of it, right? So here we go. There's your answer. So, you know, in theory, with fuels, with gasoline in a car, we could do it that way. We could say, look, there's a certain amount of energy per gallon, right? So it'd be energy content of the gasoline. So we might not give it in terms of miles per gallon. We might give it in terms of, you know, kilojoules per gallon or kilojoules per liter. That's possible we could do that. With foods, it's not that uncommon now to see foods kind of given in terms of energy content. So particularly these like little things, little snack packs where they're saying, hey, you know, you want to lose weight, so we're going to give you your cookies that you want to eat, but we're going to limit how much you get. So you don't give you a whole giant package of cookies because you'll eat half of it and get sick. We'll give you a little pack. So they could say, hey, here's a little pack of 6 cookies. But often what they do is they do it in terms of energy content. Here's a little pack of 100 calories of cookies. Now it turns out that that's 3 cookies, or 2 cookies actually. So that's what they're doing. They're telling you here's a limited amount of energy content. Here's the energy of this package, 100 kilocalories. A calorie is really a kilocalorie. We just call it calorie for short, but it's really 100 kilocalories per package. And in a sense, that's what we're doing right here. We're figuring out, you know, it's 184 kilojoules per mole, per 1 mole of chlorine. Okay. In fact, the digestion of food, or at least the metabolism of food, is actually combustion, right? So it's a very complicated process involving many, many steps, but it's essentially combustion. What you're doing is you're taking organic compounds that are made out of glucose, combinations of glucose, which we call carbohydrates, and you're breaking them up into glucose, and then you're taking the glucose and you're breaking it up into pyruvic acid, and then you're doing all these little processes, but eventually you end up with carbon dioxide and water. So the water goes through the kidneys, of course, and then the carbon dioxide is exhaled out through the lungs. So that's all combustion. It's just the actual individual steps are unique. Okay. So there you go. So there's our enthalpy. Let me see if there's one more. I guess there's, oh, okay. That's good. So we'll come back to enthalpy in a little bit. But I want to talk a little bit about calorimetry, because we did talk quite a bit last time about work, how we do mechanical work, how it involves the piston and pressure and volume changes, right? But we haven't talked about calorimetry, and that's a major topic in this chapter. So I want to make sure that by the end of the week, we've talked all about calorimetry. Okay, so this is section 5.4, calorimetry. And not colorimetry. Colorimetry is another thing. Colorimetry is the measure of light. When you measure light going through a sample, it's called colorimetry. Calorimetry is the measurement of heat. In fact, that's what the word means, right? Calor means heat. Metry means measure. Right? So we're measuring heat, right? So that's kind of cool. We can measure heat, and people have been able to measure heat for a while. There's some cool little experiments you can do at home, even if you take like a little nut, like a cashew nut or a peanut, you can put it on a paper clip, just bend a paper clip and then stick the paper clip through it. take a little cup full of water with a thermometer, measure the temperature of the water, and then burn the nut above the water and allow the heat to transfer into the water. And what you'll see is the temperature will change, and you can measure how much heat. It's not real precise measurement if you do it that way at home, but it's essentially the principle. So let's talk a little bit about what calorimetry is. So here's what we do. And there's two types. So I'm going to start with the simpler one. The first one is called constant pressure. Calorimetry, okay? Under constant pressure calorimetry, what you do is you take a thermos. And if you don't have a thermos, you can use styrofoam cups. You take 2 styrofoam cups and put one on the inside and one on the outside, just stack them. And you got a good insulator. The key to the thermos is it's an amazing insulator. Thermoses are amazing insulators. So what they do is they trap the heat inside, or they trap the heat outside. They keep heat from getting in and they keep heat from getting out, right? Remember, energy or heat is the movement of energy. Heat is the movement of energy from the higher temperature to the lower temperature regions, right? So there's an old joke, a funny joke, which is that if you think about a thermos, it can keep things cold, right? But it can also keep things hot. And so the joke is, how does the thermos know which one to do? And the answer is that really what it's doing is it's stopping energy from moving across the barrier, which is the walls of the insulator. So there's insulation here. Now, no insulator can stop heat from flowing. It can only slow it down, right? So even a really good thermos, if you give it a month, it's going to be the same temperature on the outside as it is on the inside. But it could take a couple days. Some of these thermoses are amazing. They have vacuums on the inside. They have reflective surfaces to keep light from transferring energy. Light is a way you can transfer energy. They're really amazing. So we have an insulator, right? So this right here is an insulator, a thermal insulator. And then on the inside, we have water. And this is where we're going to have our reaction taking place. So if you think, okay, hey, if there's a reaction occurring in water, what could it be? Well, it could be an acid-base reaction, right? That you could do that in water. In fact, that experiment that you guys are doing now, the determination of the acetic acid content of vinegar, that's an acid-base reaction. You're taking an acid and a base. So HCl is an acid. Dissolve it in water. Sodium hydroxide is a base. Dissolve it in water. What do they form? Acid-bases reactions form water and salt, or a salt and water. So H plus reacts with OH minus to give you water. Na plus reacts with Cl minus to give you the salt. So NaCl plus H2O. And it turns out acid-base reactions are associated with energy changes. They're not as energetic as redox reactions. So there's a reason that we don't use acid-base reactions to drive our cars or to heat our houses. They don't produce that much energy. They produce some, but not enough that it would be, economically feasible to use them to do real work, okay? Redox reactions are the chemical reactions that are associated with the greatest energy changes. So the precipitation, almost no energy change, so little that would not be practical to use that. There's a little bit, but it's very tiny, okay? So there's a reaction occurring in there. So we're gonna put an acid in there. We're gonna put a base in there and they're gonna react, right? And there's gonna be energy. Now, acid-base reactions could be endothermic or exothermic. Some are exothermic, some are endothermic. This one, it turns out, is exothermic. This one actually releases energy, releases heat, okay? So this is an exothermic reaction. And actually, I happen to remember the number. Delta H for this reaction is minus 55.6 kilojoules, somewhere around there. It's around minus 56 kilojoules, okay? So that's a pretty small number compared to the ones we looked at, minus 183, minus 890. You know, those are much bigger energy. This one's a little too small to use for anything other than just studying it. So the next thing we do is we put a thermometer in here. Okay, so there's our thermometer. Okay, thermometer measures temperature, right? And, you know, we could use more sophisticated thermometers. This is a glass thermometer that I stuck in there, but whatever. The reason it's constant pressure is because I have it open, right? It's open here. Now I could put a little lid on it to do a little bit better job of insulating, but I'll put it on loosely. And if you put it on loosely, that means the air can move in and out. So it will equilibrate the pressure. The pressure in here will be the same as the pressure out here. And so that's constant pressure because the pressure of the atmosphere is not going to change in the 30 seconds that this reaction occurs. We don't do reactions that last a year. The pressure of the atmosphere does change in a year, right? You can have high pressure, low pressure. But if we do this reaction in 30 seconds, the air pressure is not going to change. So we got constant pressure. The significance of constant pressure is it makes it easiest for it to do this. We just say, hey, constant pressure, delta H equals QP, right? Q at constant pressure. So here's how we measure Q. It's equal to M times C times delta T. Okay, and we're going to go through this a little bit here. We do have to have a negative in there, so I'm going to put a negative in there. Okay. Now, here's the idea. M is equal to the mass of the solution. Okay, so that's the water plus the acid plus the base. Okay, the mass of the solution. So everything that's in here. Okay, C is called the specific heat capacity. Typically, it's just called specific heat for short because specific heat capacity is such a long name, right? So we just call it specific heat, okay? This is a number, it's a value for the material, which in this case would be water, okay? Water has a specific heat value. Just like every material has its own density, water has a density of 1 gram per milliliter, alcohol has a density of 0.78 grams per milliliter. Water also has what's called a specific heat, and we'll talk about it in a moment. Delta T, you'll see this delta, right? We've already talked about delta in terms of delta H, delta U. That means change, right? So this means T final minus T initial. Okay, so here's the process we're looking at. We have the water, it's at some temperature. Let's say the water is initially at 21 degrees C. Okay, room temperature. Then what do? We add the acid and base to each other. Maybe we already have the acid in there and we just add the base, or maybe we already have the base in there and we add the acid. Once we add the second reactant, they start to react and they start to produce heat. The heat doesn't get produced until the reaction starts. So once that second reactant is added, starts reacting, starts releasing energy. It's exothermic, right? So what'll happen is that heat, that energy, molecular motion will move throughout the water. So you might want to actually have like a little way to stir this solution so the heat transfers evenly. So there are ways to do that. You can put a little magnetic device down here, just a little magnet with Teflon on the outside so it doesn't react. And then put a little device out here that has a bigger magnet that rotates. So as that big magnet rotates, the magnetic field will cause that little guy there to rotate on the inside and it'll mix the solution. It's called a magnetic stirrer. Okay, So what happens is heat gets moved across, and what happens? The heat is moving from the reaction into the water. So what happens to the water? The water starts to heat up, right? Heat flows from high temperature to low temperature. So the reaction is hot, the water is colder, the heat flows into the water starts to get hot. And what will happen is over time, the water will reach some temperature, and then the reaction will end, and then it'll cool back down, but it'll go up. So it might go up to 24 degrees C. Okay, it just depends whatever the specifics of the reaction are. So what happened? The water got hotter. So the thermometer is telling us how much it got hotter by. Okay, so now here's what we do. We say, look, if I measure the mass of the water, I can do that, right? All I need is a scale, a balance to do that. I can measure that. I now know what delta T is. Delta T is just T final minus T initial, which is 3 degrees C, right? So I now know what this is here. If I knew what that was, C, I would now know what Q is, right? That's all you got to do. You just got to figure out what C is, and you know what Q is. So what people do is they figure out what C is for every type of material. So what is it for water? What is it for alcohol? What is it for wood? What is it for the human body? What is it for the heart? Those specifics can be measured in order to determine Q. If you don't have C, you can't figure out Q, but if you do have it, you can figure out what Q is for any reaction. So those values for some materials are available. In general chemistry, we're usually only interested in a few materials: water, alcohol, copper, gold, iron. If you take a physics class, they might have in the table steel and wood. You know, engineering, they might have other materials. Engineering is going to have all kinds of other materials, gases and stuff like that, because you're interested in exchange of energy quite a bit. But usually it's just a few materials. For us, it's mainly just water, right? Water is the one we're most often, because we're running reactions in water. That's what chapter 4 was all about, okay? So if we do know what C is, now we can calculate Q. We measure the mass of the water, we measure the change in temperature with the thermometer, and then we measure, we know what C is, we look it up, okay? And then you've got Q. So that's called calorimetry. That's the way that we figure out the heat of a reaction. And remember, Q is equal to delta H. So we now have delta H for the reaction. Now I said for acid-base reactions, for strong acid, strong base reactions, it's this value right here, but we could confirm that. So the question then is, how do you figure out what C is? That's the key, right? That's sort of the $64 question, is how do you figure out what C is? And there are different ways to do it, and people figured that out a long time ago. 100 years ago, people figured that out. One way to do it is to use electricity. We know that electricity can be measured very precisely. If you think about it, your phone, your cell phone, has this circuitry in it that can measure voltages really precisely. It can measure electrical currents really precisely. It has that, all the sensors are built in there. Electricity is something that we can measure really, really well, just like we can measure mass really well. So all that's been kind of worked out. There is a relationship between electrical voltage and electrical current and energy. So the amount of energy is related to the amount of current and voltage. I'm not going to go through it in this course. We cover it a little bit in Chemistry 1200 if you take that. But suffice it to say that we can measure the amount of energy in electricity really easily and really precisely using voltmeters and amp meters and all sorts of devices, okay? All those things are actually built into your phones now. It's amazing. So what you do is you run an electrical current. You just put a little electrical circuit into the water that's hooked up to a device that measures the amount of electrical energy. And you just sort of run it through. And what it will do is it will heat up the water, okay? So some of the energy will heat up the water. And so what you do is you measure how much the water changes temperature, and you measure the mass of the water. So you got your delta T and your M, and then the amount of energy that went in, you're measuring that using this electrical device. So the electrical device actually gives you Q, because Q is energy, right? Heat is a form of energy. So once you've got Q, once you've got M, once you got delta T, you can figure out C. And now you know the specific heat capacity of the water. So that's not the only way that it's done. There are other ways you can do it as well. There's some very clever ways in which you can do it. You can take the heat and use it to do mechanical work, all kinds of cool stuff. But suffice it to say, we do know the value of C for many materials now. So here's what we'll say for water. So again, this is called the specific heat of water. So I'll write CH2O. It's equal to 4.184 joules per gram degree C. Okay. So that's the specific heat of water. So we do know that value right there. Now, you might say, wait a minute, you said it was water plus acid plus base. Wouldn't that be different? And the answer is yes, it is actually a little bit different. Adding an acid, adding a base to water changes the specific heat capacity of it a little bit, but very little. And we can take that into account if we want to do really precise calculations and measurements. But for the most part, we don't need to do that in this course. So we'll just go ahead and use this value right here. It'll get us close enough to the right answer that that's fine. In the lab experiment that you guys will do for thermochemistry, that's actually taken into account in the calculations. We adjust the value of C a little bit to take into account the reactants that are in there. Okay, so 4.184, just to compare it to other materials. So if I take, for example, copper, Cu is copper, it's much smaller. It's 0.385. And so the specific heat of metals is between 0.1 and 1. It's, it's usually greater than 0.1, but less than 1. They're all between there, whatever the metal is. They all kind of behave very similar. In fact, there's a cool little simple equation called the Dulong-Petit equation that allows you to estimate what C would be for any metal. But notice the big difference. Those metals are between 0.1 and 1. Water is 4.84. That's a lot bigger, right? And so that's the nature of waters. It has a very high specific heat capacity. Okay. So that will allow us to do calculations. Now that we know C, all we got to do is measure delta T, measure mass, and then we're set. Okay. So let me see. We got about 10 minutes here. So let me see if I can pull up a question. Where we actually want to figure out what the specific heat is based on some measurements. Okay. All right, so this is calculating specific heat capacity. Okay, so it says here that a chemist carefully measures the amount of heat. So notice the chemist measures heat. Of course, they got to put carefully in there. Can't do it uncarefully, right? And they raise the temperature, okay? So they tell you, this is the information that you get. There's 629.0 milligrams of the sample. Okay, so that it's a pure substance, meaning that you can, if it's a pure substance, it's going to have a specific heat that you can measure, right? If it's a mixture, the specific heat will change based on how much of each material is in the mixture. So they're just trying to tell you it's a simple, pure substance. And the temperature goes from minus 3.3 degrees C all the way up to 15.5 degrees C. Okay, so there's a temperature change, right? Right there you can see that's a temperature change. And then the experiment shows that 28.9 joules of heat are needed. And then the question is, calculate the specific heat capacity of this material, this substance, okay? So here's a picture. you've got this, I'm going to just assume it's a block of metal. We don't know what it is. It doesn't say anything that would tell us what it is, but imagine it's just a block of metal. Okay. And it's originally, the initial temperature is minus 3.3 degrees C. It's like in the freezer. Okay. And then what they do is they put heat in. Now, they don't tell you how they put the heat in, but maybe they do it electrically, put some electrical energy in. And they tell you the amount of heat is 28.9 joules. So that's how much is going in. So again, if you put energy into it, it's probably going to get hotter, right? You don't put energy into something and it gets colder. You put energy in and it gets hotter. So what's going to happen is it's going to get hotter, right? So how much did it get hotter by? Well, the final temperature was 15.5 degrees C. Okay. So let's go ahead and calculate the specific heat capacity. So Q equals mc delta T. By the way, your textbook, not Alex, but the textbook uses a different symbol for specific heat. They use an S. S for specific. And they typically put the S before the M, SM delta T. I like MC delta T. That's the more kind of traditional symbols to use, but your textbook uses SM delta T, but it doesn't matter. Specific heat times mass times change in temperature. Okay, so what do we know? We know the mass, so I'm going to go ahead and put that in there. 629 milligrams. Notice I didn't convert it to any other units, but we'll take care of that in a little bit. And then, okay, but we want to find C. So what do? We divide both sides by M, and we divide both sides by delta T. Right? Because then the masses cancel, the delta T's cancel, and you've got C. So C is Q over M delta T. Okay, so let's go ahead and put everything in there. We've got 28.9 joules. We've got a mass of 629 milligrams. And then we got a delta T of 15.5 minus 3.3. Minus a minus, right? Remember, it's final minus initial. So it's 15 minus a minus 3.3. So that's equal to 15.5 plus 3.3, which is 18.8. So 18.8. Okay, specific heats are positive. You're not going to get a negative. So if you calculate that delta T and the delta T is negative, it got colder, that would be because they took heat out. And if you take heat out, Q is negative. So a negative divided by negative is positive. But the specific heat should be positive. Okay, so 28.9, just be careful if you are doing this in your calculator. You divide it by 629. Oops, I keep making mistakes. Sorry, 28.9 divided by 629.0. Divided by both of them. So now divided by 18.8. And so here we go. 0.00244 units are joules, milligram, degrees C. Now that's a pretty small value. As I said, metals are 0.1 to 1. So how did we get something that was so small? Well, the reason I said it was 0.1 to 1 and water was 4 is that that was joules per gram degrees C, not per milligram degrees C. So if we want to have it in a value that's in that sort of range that I spoke about, 0.1 up to water is 4, you got to have it in joules per gram degrees C. So pay attention when they ask you these questions, if they give you any hints on the units. A chemist carefully measures it. What can the chemist report for the specific heat? So it doesn't actually tell you what the units are in. So presumably you could leave it in joules per milligram, but typically it's joules per gram degrees C. So let me just at least show you. Oops. Let me save that. 00244. Let me just show you how to deal with that. I'm sorry. 244 joules per milligram degrees C. This can be a little bit tricky, but let me show you how to do it. What we want to do is we want to convert milligrams to grams. Okay, so here's how you can do that. Remember, milli is 10 to the minus 3. All right, centi is 10 to the minus 2, deci is 10 to the minus 1, micro is 10 to the minus 6, so it's 10 to the minus 3. So 1 milligram is 10 to the, 1 milli is 10 to the minus 3 grams. So now let's do the conversion. We want to get rid of milligram, right? So put 1 milligram up on the top so that they will cancel, and then put 10 to the minus 3 grams. And then mathematically, dividing by a number is like multiplying by the 10 to the negative of whatever you have. So in other words, dividing by 10 to the minus 3 is like multiplying by 1,000. So what that does is it multiplies by 1,000. So our milligrams are gone, and you move it over 3 places. 1, 2, 3 is 1,000. So 2.44. And now you have joules per gram degrees C. And so now we know it's not a metal, right? Because we said that metals were 0.1 to 1. Water was 4.184. This is probably alcohol. Alcohols are typically around 2 to 3. Okay, so it's probably an alcohol. They don't ask you to identify what it is. But if we had a little table and it said, hey, it's 2.1 is this material, 2.4 is this other material, and 2.7 is this other material, you'd pick the material that was 2.4 because that's pretty close to it. So there's our specific heat, right? So that's kind of the first type of problem they have you do, which is, they don't tell you how the energy was measured, but somehow we measured the energy. They give you the mass of the material, they give you the change in temperature of the material, and then you find the specific heat capacity. Okay. And there you go. So you'll need to play around with Alex to see what units it wants it in. If we were going to leave it in milligrams, it might be a good idea to put it in scientific notation. So if we were going to leave it milligrams degrees C, this is such a small number. Let's put it into scientific notation, right? Left is positive, which means if you're moving the decimal point to the left, the power of 10 will be positive. But if you're moving the opposite, if you're moving to the right, it becomes negative. So 2.44, we moved it 3 places, right? So times 10 to the minus 3 joules per milligram degrees C. That's a pretty odd unit to have milligrams, so you're not likely to see that. You might see millijoules per gram degrees C. You might see kilograms in the denominator, but typically not milligrams. Okay. So either way, either 2.4 here or 2.44 times 10 to the minus 3 per milligram. And there you go. Okay. So we'll keep working on calorimetry tomorrow. And then we only have one more sort of topic left for this chapter, which is heats of reaction, standard heats of reaction. So we'll talk about standard heats of reaction probably. We might actually hit it a little bit tomorrow if we have time. If not, certainly we'll do it on Thursday. The next objective is chapter 10. We go from 5 to 10, which is gases. So we'll start talking about gases. This is a pretty lengthy chapter. 10 is a lengthy chapter. So if we start talking about that on Thursday, that'll be perfectly fine to kind of get you started on that. And again, reach out to me if you have any questions, and have a great day, you guys.
Thank you.
Thank you, Professor.
Good day, Professor. Professor, I have a quick question for you.
Sure. Hold on one sec. Let me stop the